thank you very much. It's a really great honor and pleasure to be here, to speak here, and to serve as a warm-up band for Lauren and Carolina. So I'd like to tell you about minimal kinematics. And the point of departure is the moduli space, M0n, of n labeled points on the line. And this is the projective line or Riemann sphere. So each point is given by homogeneous coordinates. And these are the columns of this 2 by n matrix. And this is up to projective transformation. So I can fix 3 of the points to be, to be 1, 0, 1, 1, and 0, 1. And then the remaining n minus 3 points are unknown. So I have n minus 3 unknowns. So this moduli space is a very affine variety of dimension n minus 3, the n minus 3 degrees of freedom. Now, officially, this is constructed by taking the open Grassmannian. So this is the space of 2-dimensional vector subspaces in an n-dimensional vector space. And open means that I require the Plücker coordinates Pij. So Pij is the 2 by 2 subdeterminant here to be non-zero. And this ensures that the points are actually distinct. Now, much of what I say is contained in this paper with Nick Early and Anna Alfesto, who's a grad student at Leipzig. And after the talk, Nick will be very happy to answer your questions. Now, M0n is also geometrically the complement of an arrangement of hyperplanes, namely n minus 1 choose 2, hyperplanes xi minus xj, right? This is simply the requirement that the points are distinct. So for example, for n equals 5, this is an arrangement of 6 lines in the plane, complex projective plane, given by the equations xi equals xj. And this is how it looks. Now there are 4 special points in this arrangement where we have triple intersections. And what mathematicians like to do is to replace these triple intersections by a blown-up situation where we only have 2 pairwise intersections. And this leads to the real surface, the surface M05 bar. And the real picture now is that there are 12 pentagons, right? So here in the original diagram in the plane, you saw 12 triangles, 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11, 12, 7, 8, 9, 10, 11, 12. This is in the projective plane. So these 12 triangles in the blow-up get replaced by 12 pentagons. Now, pentagon is a 2-dimensional convex polytope, and it's the 2-dimensional isosahedron. So here's the same picture in 1 dimension higher. So the moduli space M06, a 3-dimensional space, is the complement of 10 planes in 3-dimensional projective space, CP3. Now, if we concentrate on the real points, then this space is glued from 60 isosahedra. So a 3-dimensional isosahedron is a 3-dimensional convex polytope, simple convex polytope with 14 vertices, 21 edges, and 9 facets. So the 14 vertices correspond to the 14 triangulations of a hexagon. The facets correspond to the diagonals. So these are the coarsest subdivisions. You take 60 copies of this, and you glue it together, and that makes this 3-dimensional space. And this is our space M06, and there's a typo that should be M06. And this is the 3-dimensional version of this simpler 2-dimensional picture. So this is the moduli space of n points, labeled points on the projective line or Riemann surface. Now I'm here to learn from you, right? So I'm really here to study physics. I just turned 62. And for the first 60 years of my life, I safely stayed away from physics. So this is more or less my first physics conference. And so I'm studying, right? So on this picture here, more or less, you see this integrand. So this is the reciprocal of P12 times P23 and so on cyclically around times Pn minus 1. So these are our Plücker coordinates. So these are the xi minus xj. And in this Koba-Nielsen string integral, we are having a kernel here. So this is a monomial in these Plücker coordinates Pij raised to some power epsilon times Sij. Now mathematicians, small quantities, when we teach calculus, they're called epsilon. I know in your community sometimes it's called alpha prime, but for me it's epsilon. And then the Sij are parameters called Mandelstam invariants. Now then, for good measure, we scale this by epsilon raised to the dimension of our space, and we're integrating out the moduli space, and we get a function on these parameters, on these invariants. Now, as you well know, the Mandelstam invariants encode kinematic data. They satisfy the condition that they form the entries of a symmetric n by n matrix with zeros on the diagonal and all row sums and column sums 0. So those are the momentum conservation relations. Okay, so this is the integral. Now, this is, of course, a complicated transcendental function of the S's, but we get something easier and nice if epsilon tends to 0. So for epsilon tends to 0, we get a quantity called Mn. This is the bi-adjoint scalar amplitude in phi cubed theory. And this is the leading singularity. Now, this is a rational function of degree 3 minus n, negative our dimension. And so this has very, very nice expressions. So for example, here is one formula. So this M6 can be written as a sum of 14 terms, each a reciprocal of a cubic expression. So the Sij we've already seen, and then we have 3 indices like S123. This simply means S12 plus S13 plus S23. Okay? But we have to take this carefully because really this is only defined up to momentum conservation. Right? So this is a rational function in the S's, homogeneous rational function, but it's a rational function on this space. Now, the 14 terms correspond to the 14 vertices of our associahedron. So there's one summand here for each triangulation, and the combinatorics here of this denominators tell you about putting in the diagonals to make a triangulation. And of course, there are 60 different cyclic orders. So 6 people go to a party or restaurant. How many ways can they sit around the table? Well, there's 60 ways to sit around the table, corresponding to the 60 associahedra that make up our ambient space. But for one cyclic ordering, we have this formula. Now, this looks deceptively simple, as we learned in Shruti's talk yesterday. As soon as you take denominators, all hell, if you clear denominators, you get a rather long and complicated numerator. So there's still a lot we can study about this rational function, and we've heard about some of this in the conference already. So I do study physics, but I'm more familiar with statistics. So I got into this game by seeing a connection between a structure in statistics and the scattering equations, and we worked on this together with Simon Thelen a couple years back. So here we have the scattering potential, the CHY scattering potential. So this is a function L on our moduli space. So it's a function on the Pij, and the Mandelstam invariants Sij, they serve as the coefficients now. So it's a linear combinations of the logs of these Pijs, which are non-zero. Now, this is actually well defined on M0n. So you recall from the first slide that M0n really is the Grassmannian modulo the torus. So there's a scaling. And it turns out that the momentum conservation relation, they precisely ensure that this is well defined on M0n. So another way to say this is you can rewrite this expression in terms of logarithms of cross ratios. So the Pij are not valid coordinates. They're not well defined on the moduli space. But what's well defined is cross ratios like P12 times P34 divided by P13 times P24. And momentum conservation is sort of by design makes this a well-defined function on our moduli space. Now also throughout this talk, I fixed this gauge. So I fixed the particular 2 by n matrix that we saw at the beginning. And in that matrix, some of the minors are just 1. Right? So you saw an identity matrix, and the determinant is just 1. So I'm going to only concentrate here. So the logarithm of 1 would be 0. Right? So I can drop all the terms where Pij involves none of the unknowns. And what's left is this set S. So these are pairs Ij, where I and j is not 1, 2, and I'm only going up to n minus 1. So those are the non-constant 2 by 2 minors of the matrix we started out with. But as I said, my point of entry was statistics, in particular the study of likelihood functions, maximum likelihood estimation. And in statistics, this L of p is called the log likelihood function for obvious reasons. Now, so that got me into this. So I saw the similarity. Now, there's some minor differences, right? So in physics, if you have a potential, you want to minimize it. In statistics, if you have a log likelihood function, you want to maximize it. But really, we care about the critical points. And we have the following familiar theorem. So if the Sij are general, maybe let's say complex numbers, then the log likelihood function has n minus 3 factorial, that is to say dimension factorial, many complex critical points. Now, moreover, if the Sij are all real numbers, then all the complex critical points are real. Okay, and this has been discovered and rediscovered many times, and in combinatorics, this is usually attributed to Varchenko. It's known as Varchenko's formula that says if you have a hyperplane arrangement and a corresponding log likelihood function, then the number of complex critical points will be the number of bounded regions in the hyperplane arrangement, and you also have this reality state. Okay, so this is the scattering potential. Now, how about the amplitude? Well, the amplitude can be written in terms of these critical points. So the same expression mn, our rational function that we saw, up to sign is the sum over all critical points p hat. And what I'm going to do is I'm going to take my integrand as squared. So this is the Park-Taylor integrand squared. I divide by the Hessian of the log likelihood function, right? So the log likelihood function, the Hessian is the determinant of the symmetric matrix of second partial derivatives. And so this is also a rational function. So I evaluate this rational function at each critical point, p hat, and then I sum out. Now, by Galois theory, this is invariant, right? And it becomes a rational function, and this is precisely the biojoint scalar amplitude we saw. Now, one disadvantage here, and this you also see in the clearing denominators efforts that were alluded to in Shruti's talk, the number of summands is very large, right? So n minus 3 factorial is a very large number. So this makes this actually a surprisingly complicated rational function. And somehow we'd like to do something easier, right? So the question I like to discuss here is, wouldn't it be nicer if we had only one critical point? But that's the question you can ask for any polynomial system, right? So I have a system of polynomial equations. It has many, many roots. So one thing I could do, I could struggle and compute all these solutions. Another thing I could say, well, I don't want to do that, right? I'm going to rather replace my system of equations by another system that has only one solution. So this is what I'm going to do now. And this is the topic of this talk. So this is called minimal kinematics. So the term minimal kinematics comes from this paper by Freddie and Nick called Minimal Kinematics, an all k and n peak into the positive tropical Grassmannian Kn, published 3 years ago. and I will not speak about the positive tropical Grassmannian today. I'm going to think we might hear about at least the positive Grassmannian a little later. And also, for the most part, I'll concentrate on k equals 2. Okay? Let me state the theorem. So the first theorem in the paper with Nick and Anael says the following. Choices of minimal kinematics on our moduli space are in bijection with a certain family of graphs. There's a family of graphs called two trees. So two tree is a kind of graph, and these are two trees on the vertex set 1 up to n minus 1, abbreviated bracket n minus 1. Okay, so this is the theorem, so I'm going to explain this theorem now. Now, to explain this theorem, I need to define the red term. I need to define minimal kinematics, and I need to define the blue term, which is two trees. Okay, so let's look at any subset T of our set S. So S are the relevant indices in writing down this scattering potential. So for every subset T, I can look at the subsum where I only take the pairs in T. So following on Shruti's talk, I set all the other things to 0. So I'm just zeroing out the Sij that are not in the chosen set T. Okay? So then I'm going to say that set exhibits minimal kinematics if this new log likelihood function, this new scattering potential, has exactly one critical point. And it is inclusion maximal with this property, right? So this means I start out with my original scattering potential. It has many, many critical points. I set some s's to 0. I set some other s's to 0. And I say beep the first time I have only one critical point, and then I stop. I'm going to call that minimal kinematics. Now then, of course, there's no sum. There's only one critical point. And that critical point then will be a rational function in the Mandelstam invariance S. Right? So that's my definition here of minimal kinematics. Now, what's a two tree? So this is a class of graphs. They're not trees. They look like trees, but they're not trees. And they're inductively defined as follows. So if I have two vertices, then I glue in a single edge. This is in a two tree. Now, any two tree on k vertices is obtained from a two tree on k minus 1 vertices as follows. You pick any edge, ij, from the small tree, and you connect the new vertex to the two endpoints of the chosen edge. Right? So if you choose the edge ij in the small tree, you just throw in two new edges, ik and ij. Very simple definition. So inductively, you add two new edges any given time. So let's see some examples and summarize some basic facts. So what I'm going to do is I'm going to disregard the original 1, 2 edge. So I'm only going to, count the number of edges that I added in. And so with that count, every two tree on n minus 1 has 2n minus 6 edges, an even number of edges. Now, if I look at these two trees together with their labeling, then the total number is 2n minus 5 double factorial. And double factorial is the product of odd integers, 1 times 3 times 5 times 7 until 2n minus 5. Now, if I disregard the labeling up to symmetry, then the number of two trees is given by this sequence. So here, if n is 4, 5, 6, 7, then this is the sequence. And this can be found on the online encyclopedia of integer sequences. So two trees are well-studied objects in graph theory, right? So for example, for n equals 6, so this is our M0n, M06 space, glued from 60 happy sociohedra. There are two non-isomorphic two trees. There's the planar two tree, T1, and there's a non-planar two tree, T2. And here, this is the 2n minus 6. So these are the edges in this notation. Now, when I draw a two tree, what I'm going to do is I'm going to draw n minus 2 triangles. So recall that I always make two new edges, ik and jk, by hooking it up with an earlier edge ij, so they form a triangle. And then as an artificial dummy vertex, I add a triangle 1, 2, n. So remember, n was not used here. So I'm just, for good measure, stick on a triangle 1, 2, 6. So this 2 tree is visualized by this picture, and the non-planar 2 tree is visualized by this picture. So those are graphs. They're not trees, but they're sort of trees of triangles. Again, our theorem says that this is exactly the combinatorics for minimal kinematics on M0n. Now let's examine the formula, right? So let's look at our two examples, this one and that one, and actually write down the unique critical point. And in each case, I'm going to write the 6 coordinates p hat for the unique critical point. So here, p1, 3 hat is the 1, 3 coordinate written in Mandelstam invariance, at the critical point. Okay, and this is see this linear divided by another linear, here cubic divided by cubic, right? And then here down here is the analogous thing for this 2 tree, and this is indexed by the edges, right? So here the indices are the edges, the non-trivial edges of our tree. Now what I want you to notice is that these rational functions are very, very special, right? First of all, the numerator and denominator factors into linear forms, right? So every numerator and every denominator is a product of linear forms. Second, all linear forms have positive coefficients, okay? So these are linear forms with positive coefficients. Well, now let's plug this into the amplitude, right, to just see how this goes, right? So if I take my, this is again the original biojoint scalar amplitude with its 14, that is to say, Catalan many terms. Now I'm setting those 3 things to 0 because these are the non-edges in this tree, right? So 2, 4 is not an edge, 2, 5 is not an edge, and 3, 5 is not an edge, so those are 0. So this T1 exhibits minimal kinematics. And after the substitution, then this expression becomes this expression. Okay? So again, the numerator here, a product of positive linear forms of degree 3. The denominator, a product of positive linear forms of degree 6. So the total degree is -3. The negated dimension of the moduli space. So everything is a product of positive linear forms. So why? Why do we see positive linear forms here appearing in each expression? In the critical point and therefore also in the amplitude. Now the explanation is given by a theorem due to Kapranov, Misha Kapranov, now at a physics institute in Tokyo, and Juni He here from Princeton. Let me call this positive linear geometry. Now this was discovered by Kapranov in the 90s in a very different context. He refers to this as the Horn uniformization. And Horn here was a German mathematician in the 19th century, and he taught the ordinary differential equations. So he was a differential equations professor in the 1860s, and he studied hypergeometric functions. So we heard about GKZ hypergeometric functions. So this Kapranov came up with this Horn uniformization. Now this was then further developed by Juni He a couple years ago, and then we took this back into statistics, where complex numbers are real and positive in this paper, and I think this paper is a good reference to read about this theorem. So it says the following. For any very affine variety X, so very affine means it's a closed subvariety of a torus. So X is defined by a system of Laurent polynomial equations and M unknowns. Then the following 3 conditions are equivalent. First condition is the Euler characteristic up to sign is 1. So just as a topological space, this open complex variety has Euler characteristic 1. And that Euler characteristic is equal to the number of master integrals. So in the Feynman discussions on Monday morning, this is the number of master integrals, and there's only one. Second condition is the log likelihood function on x has a unique critical point p hat, and the equivalence of 1 and 2 is not so difficult, knowing the relationship with the Euler characteristic. So that's the second condition. So on any very affine variety, you can write down a scattering potential or log likelihood function. But the meat is in the third part. So it says x has a so-called Horn uniformization. And this is a formula for the unique critical point. And in the ingredients are H is an integer matrix with m columns, and lambda is an integer vector of length m. And the pair H lambda is an invariant of the variety. And the formula works as follows. So H is a matrix. S is the column vector of unknowns, in our case, the Mandelstam invariant. So H times S is a column vector of linear forms in the S's. I have to tell you what this means. So I have a vector raised to a matrix. What does that mean? Well, vector raised to a vector that's a scalar, right? So if I have A to the U times B to the V, that would be the vector AB raised to the vector UV, right? So vector raised to a vector is scalar. Well, vector raised to a matrix is simply the vector. We use the column vectors of H, so this is a vector, right? So this is a vector of length m. The star is the entry-wise or Hadamard product. So I multiply the m coordinates of this vector coordinate-wise with the coordinates of that vector, okay? And so as I said, in our example, in our application, m is 2n minus 6, and s is the column vector of Mandelstam invariance. So this is the shorthand notation for these formulas. Right? So these the structure, the combinatorial structure of these formulas is summarized in this expression. Now let me illustrate this a little bit further by actually writing down the Horn matrices for our two examples. So for our planar example, this is the Horn matrix, and for our non-planar example, this is the Horn matrix. And you can see that in every row the signs are constant. Right? So this leads to positive linear forms. So in this example, there are 9 by 6 integer matrices. So if you take these matrices, you plug them into this expression, then you get these formulas. Okay? Okay, so these are the Horn matrices. Let me give you yet another reformulation of the same thing. Right? So in our context, we can also reformulate this as follows. So let me write bracket Sij for the sum of all Mandelstam invariants, SLM, where Lm is a descendant of the edge ij in my 2 tree. So there's a natural parent-child relation among the edges, right? Because I'm creating new edges from old edges. So I'm starting with ij, and I make ik and jk. Those are the children of ij. And then I'm summing here over all descendants. So then I can also write this as follows. So the Lm coordinate of our unique critical point is the product. In the numerator, I have bracket Sik, it's the sum, and then divided by Sik bracket plus Sjk bracket. And the product runs over all ancestral triangles ijk of the edge Lm. An ancestral triangle, it's a triangle earlier on, right? So this means Lm is a descendant of either ik or jk. So here are the definitions. So descendant refers to transitive closure of parent-child, and an ancestral triangle is exactly what you think it is. Okay, so this formula is equivalent to this, and to this. Okay? So in this context, minimal kinematics has a very, very nice combinatorial expression. But in fact, this is true in general. Whenever you have scattering potential, something that's like a sum of logs, and if it is the case that there is exactly one critical point, it will be given by this formula. Now let's take this in the last 10 minutes and take it back to amplitudes. So let me state a theorem without having given you the definition. So I'm going to give you the definition afterwards, but I'm going to state a theorem first. So for every two-tree, I can define an amplitude, mt, and the amplitude associated with the two-tree is the following product. So I multiply over all triangles in the two-tree, but now I have the sum in the numerator, sik plus sjk bracket, and then I take the product of the brackets in the denominator. This is a homogeneous rational function of degree 3 minus n, our negated dimension. Okay, so I will now define mt, and then that will be a theorem. So for example, for this two-tree, the expression looks like this, and this is a rational function homogeneous of degree minus 3. So let me give you the definitions. So first, a little metroidal definition. So given the two-tree, I'm going to introduce an n minus 2 by n matrix. And the rows of this matrix are the so-called circuits. So every ijk represents a circuit on my original 2 by n matrix. And I'm going to put in the row of this matrix pjk. Ei is the ith unit vector minus pikej plus pijek for each triangle. So for example, the first row corresponds to the 1, 2, 3 triangle, 2, 3, 4. So another way of saying this, in each row we have Cramer's rule for computing the kernel of a 2 by n matrix. So indeed, the rows of this matrix span the kernel of the original matrix that defines my point in M0n. Now, because that is so, the maximal minors have a very particular structure. So if you delete 2 columns, if you delete the I and j columns of this matrix, then you get a square matrix. And the determinant of that square matrix up to sign is pij times some global determinant delta. Right? So delta is the greatest common divisor of all the maximal minors of this matrix. So in our case of the two-tree, this delta is an explicit monomial in Plücker coordinates. And here the exponents come from this quantity Vt. So Vt of ij is the number of triangles containing ij. Okay? So this is the delta. And Jarek can tell you later where this appears in the physics literature. So now I'm going to define the integrand. So this generalizes the Park-Taylor integrand, right? So now I'm going to define the integrand for our two-tree to be the following. So I take delta squared times the product over the ij, pij over all triangles. And again, this has a formula in terms of my v function. And now I'm going to define the amplitude by the previous formula. The amplitude is simply the integrand squared divided by the Hessian at the unique critical point. There's no sum. There's only one critical point. I'm defining it as before as I squared divided by the Hessian at the critical point, and then by the theorem that's equal to this expression. Now, if it so happens that the two-tree is planar, as it is in this example, then this is the restriction of Mn to T. Then this was our previous amplitude. But if we're non-planar, this is new. So in the last 4.5 minutes, let me talk about hypertrees. So hypertrees are collections of triples that look like a two-tree but are not. Right? So a hypertree is a collection of triples, n minus 2 of them, such that every index appears in at least 2 triples, and they're spread out enough. There's a spreading out condition. Now, this comes from an article by Kastrave and Tevelev a couple years back. So hypertrees have the same number of triples as two-trees, but they're not hypertrees because two-trees do not satisfy the first condition. But everything I said in the last 3 minutes, the matrix MT, the integrand IT, and the amplitude little m are defined as before. So exactly the same definitions work. So let's see an example. So this is known as the octahedral hypertree, right? So this is the hypertree with the triangles 1, 2, 3, 3, 4, 5, 1, 5, 6, and 2, 4, 6. So here's our circuit matrix. But now the hypertree divisor, the greatest common divisor of the 4x4 minors, is an irreducible hypersurface in our moduli space, and is defined by this irreducible polynomial. Now, these hypertree divisors were a very big deal a couple years back in birational algebraic geometry, because they were used to prove that the birational algebraic geometry of M06 is much richer than previously thought. So in particular, Tevelev and Castreve solved a long-standing problem by Fulton. Now, interestingly, hypertrees are precisely on-shell diagrams in your community. So non-planar on-shell diagrams, non-planar Playbig graphs are a thing in the literature. So here is one reference on non-planar on-shell diagrams, and they are precisely the same thing as the irreducible hypertree. So I like to point to a very remarkable paper by Evgenia Tevelev called Scattering Amplitudes on Stable Curves, where in the last section he proves this equivalence, but he does many, many, many other things. So anticipating the 1 minute sign from my chair, I'm going to slowly wrap up. So of course, as I said, for hypertrees, we can do exactly the same thing as for two trees. So for example, we can define an amplitude, but now there's not just one critical point, there's more. So in our octahedral example here, the maximum likelihood degree, the number of critical points is 2, and summing over 2 critical points, again, you get a nice amplitude formula reminiscent of the one for the isosahedron. But here, the relevant polytope is not the isosahedron, but the rhombic dodecahedron. So there's a wealth of interesting amplitudes coming not just from two trees, but also from hypertrees. And I think it's a very, very good research direction to dig a little bit deeper into Tevelev's work and see what this might mean for amplitudes. Okay, so this is the end of it. So in the combinatorics community, we know, and we'll hear again in the next talk, that the physics of scattering amplitudes has been very inspiring. In particular, the combinatorial structure and the combinatorial study of this and other moduli spaces has been very, very fruitful and inspiring. In this talk, I discussed one particular aspect of this. So I gave a bit of a review and an introduction to minimal kinematics here on the M0n case, but you can do this on other spaces. But one message is that minimal kinematics builds on a beautiful work of Her and Kapranov, known as Horn uniformization. Thank you for your attention.
Thank you very much, Bernd, for a very inspiring talk. Questions? Okay.
So that Horn uniformization works also for discriminants. And discriminants come with stratification by the singularity type, by the degeneracy type. So what is the preimage of those strata?
Okay, so that's correct. So this, so there is a way of packaging this in terms of a certain A discriminant, and that's how it occurred in Kapranov's work. But in this setting, so I completely agree with you, there's something called the Euler stratification. So the Euler stratification tells you, as the parameters vary, how much does the ML degree dip on various strata? How many fewer master integrals do you have on various strata? And in some situation, 1 is the smallest, right? But in this context, I'm sort of turning it around. I'm saying I'm starting from a situation where the degree is 1 to begin with, so it can only be 1 or 0. So this is a very controlled situation where we sort of understand the stratification, but by definition. So from a stratification point of view, we're doing something simple here. The A discriminant that lies in the background is for more complicated A, but this doesn't have bearing on the degree here.
Well, my question was the general understanding of the general discriminant.
In a sense, yes. In a sense, yes. So you can build Horn matrices, and and minimal kinematics from any discriminant. So you take any A discriminant, you can sort of turn it around from Capano's construction and build such a situation. But it will not, but this result will not have any bearing, as far as I can tell, on the Euler stratification. That would be relevant, you know, for example, in Landau analysis.
Okay, Mattel.
Very nice talk. I wanted to ask, is there a way to construct age explicitly from this theorem? And if so, is it manifest that each row has the same sign? And
Yes.
that was the major property that
So
you
the
needed for
answer
this?
is yes. And this is h. So if you look at the exponents, so all the exponents are, you know, plus minus 1. So you unravel the 0 plus minus 1 exponent. So you take this formula and write it as a matrix, you get the matrix. Right? So this expression is equivalent to writing the matrix.
Yeah, I was asking
so the answer
from the
to your-
theorem to the corollary whether there was it was an easy way to go, or if it was very special to the two trees that you're considering.
In this case, it's fairly explicit. Well, I mean, one should always be careful using the word easy, but it's worked out in the paper.
More questions? I have a question. So is there something like next to minimal kinematics when you can?
Yeah, that's so NMK and NNMK. So I would say yes, in some sense. As soon as you have, for example, 2 critical points, well, the next thing would be not 1 critical point, but 2 critical points. But that's already quite more difficult. So there's no such, as far as I'm aware of, there's no such simple to state a situation. There were some subsequent studies. For example, there's a study by a fellow named Arthur Bick, B-I-K, who lives 200 meters from here and on the institute grounds at the moment. So there are some works in the algebraic statistics community, but there is no super clean formula like this Horn. So it doesn't get, I mean, this is about, yeah, so it's nothing like this very elegant, simple formula. But I would say next to minimal kinematics would be ML degree 2 critical points.
Okay, any more, Nick?
There was something we considered like that. With Freddie, there was something like that, and I could tell you about that a little bit later.
Okay, nice.
Something else like that. Thanks.
More questions, comments? If not, thanks a lot, Bernd, again.